All right, so let's do an example that uses finding a tangent plane to some surface that I give you. Okay, so we've got this 3D surface uh, where the z's are defined by x cubed plus x squared y cubed minus 2y squared. And off the top of my head, I have no clue what that thing looks like. But um, you know that the point 1, 2, 1 is on it. And really, to find the tangent plane approximation, you don't actually have to know the 1, 2, 1 right off the bat. You could just be given the 1, 2, xy equals 1, 2, and then plug it in to get the z value, right? So that third 1 there is the kind of bonus knowledge that saves you a little bit of time of plugging in the 1 for x and the 2 for y to get the z equals 1. Now we learned from the big proof, the first proof that we just did a little while ago, that the tangent plane is given by this equation, f sub x at x naught y naught, x minus x naught, plus f sub y, x naught y naught, y minus y naught. Okay. So it should kind of feel like point slope form, except that it's got an x. So this part should definitely look like point slope form. Notice this is all one term. It's the slope in the x direction of x naught y naught. So it shouldn't be too much of a conceptual leap to say, well, this is like the multi-dimensional point slope form. So instead of a tangent line, you get a tangent plane out of it. So let's figure out what it is. Now the x naught y naught that we're using is 1, 2, and the z naught is 1. So let's find f sub x. So f of xy is this thing up here in the box. So f sub x is going to be 3x squared plus 2xy cubed. So f sub x when xy is 1, 2 is going to be 3 plus 2 times 8. So 16. So that's going to be 19. So this right here is going to end up being a 19. And then let's figure out f sub y. F sub y is going to be 3x squared y squared minus 4y. So f sub y at the point 1, 2 is going to be 3 times 4, 12 there, minus 8. So that'll be 4. So then this guy right here is going to end up being 4. And that's all we need. So we just plug in now. Z minus z naught, well, z naught is 1. The slope at the point where I'm looking is 19 in the x direction. X minus x naught, what's x naught? That's 1. Plus, and then the slope in the y direction is 4 at that point. Y minus y naught, what's y naught? 2. And then you can simplify a little bit if you wanted. So it's z minus 1 equals 19x minus 19 plus 4y minus 8. And then let's see, what do we get if we clean this up? We could get everything on one side, so it'd be like 19x plus 4y minus z. And then I've got a 19 and 8. Let's see, that's going to be negative 27, and then add 1. So minus 26 equals 0. So there's the equation of the tangent plane at that point. Now, let's say the surface looks like this, right? Just like I draw every 3D surface that's general. And let's say that the point that we just looked at, so down here, this point directly below it on the xy plane, that's the 1, 2, and then the z down here is 0. And when we plugged in 1, 2, we got 1, 2, 1. And so we've got this tangent plane right here, right there. So the thing that's good about a tangent plane approximation is that sometimes the function you're working with is really hideous. And so what you could do to find But you might be able to find a tangent plane at a certain point somehow using, if it's a nice point and happens to have good derivatives there. Well, you don't have to keep calculating all these function values if you don't want. You could calculate approximations. So if I pick a point close to 1, 2 down here in the xy plane, and I plug it in, I'm going to get something on the tangent plane that's reasonably close to whatever it would have been on the actual surface below it. In this case, it looks like it's below it to me. So in this case, we're looking at 1.01, 1.99. So use it to approximate the value of f. Well, that's the z value when x is 1.01 and y is 1.99. Now that's easy enough to plug into here because this is a pretty straightforward polynomial. But the nice thing about a tangent plane approximation is you don't have any cubes or squares to worry about or trig functions to worry about. It's always just going to be some constant times x plus some constant times y plus some constant times z plus some constant equals 0. So it's easier to plug these things in if you have a lot of them to plug in, and you know that it's a reasonable approximation. So if I plug in 19 times 1.01 plus 4 times 1.99, the z is what we want, minus 26 equals 0. Then we can figure out what that equals. So let's see. 19 times 1.01 plus 4 times 1.99 ends up being 27.15 minus 26 minus z equals 0. So I'm going to bring the z over. And so if we do that, that's 1.15 equals z. So the approximation for f of, what was it, 1.01, 1.99 is about 1.15. Okay, let's actually just see what it is really. So if I do 1.01 to the third plus 1.01 squared times 1.99 to the third minus 2 times 1.99 squared. Let's see what we get. It's pretty close to 1.15. Not bad for totally making up this example on the fly. All right. By the way, another term used for tangent plane approximation or tangent plane, it's also called the linearization. Because linearization means just finding some linear function that matches it. So you can apply it to multiple dimensions. You could apply it to a 10-dimensional thing if you wanted to. You just have 19x1 plus 4x2 plus something x3 plus something x4, blah, blah, blah. So, okay, I hope this helps a little bit, and I think that should set you up for the 9-4 handout. All right, take care, and I'll see you guys soon.